Okay, so next let's talk about proofs by cases. So basically, proofs by cases are situations where the hypothesis of the problem, the thing that you have to assume in the problem, can be broken into a discrete number of possibilities. Hopefully, a relatively small number of cases. There are instances where there are instances of proofs that involve thousands or maybe millions or billions or trillions of cases to be checked. And maybe those cases are checked via some sort of computer algorithm. But for the sort of things we're going to do in this class, maybe it's the sort of thing that breaks up into, less than 5 or 6 cases, okay? So again, we're typically wanting to prove statements of the form A implies B. And it's when you can break the hypothesis up here. So whatever A is, the hypothesis of the problem, whenever you can break that up into a number of possibilities, that's when a proof by cases may be appropriate. So some typical scenarios are, if in the hypothesis you're assuming n is an integer, well, integers can be either even or odd, so sometimes it can be helpful to break your proof into considering those two possibilities separately. So consider the case when n is even, consider the case when n is odd separately. If in your hypothesis you have a real number x, one way to break that up into 3 discrete possibilities is to consider the case when x is negative, or when x is 0, or when x is positive. Another way, whenever you're dealing with real numbers, that sometimes applies, is you can break the two possibilities. So if x is a real number, you can break that up into x is a rational number, so you can write it as a fraction of integers, or it's an irrational number, so one of these weird numbers like pi or e. When you're dealing with, let's say you're in your hypothesis you have 2 integers, one way you may break that up is to say, well, m and n are both even, or m and n are both odd, or a third possibility is m and n have opposite parity, so one of them is even and one of them is odd. If in your hypothesis you're dealing with the remainder upon division by an integer, then as you know, when you divide by 5, for example, the remainder can be 0, 1, 2, 3, or 4. So there are 5 possibilities for the remainder there. And if you're in general, if you're dividing by n, there are n possibilities for the remainder, 0, 1, 2, all the way up to n minus 1 is the biggest the remainder can be. So that may be another way that you can break up your hypothesis into some discrete cases. So if you're dividing by 3, for example, you would only have 3 cases to check. So that's kind of nice there. Okay, so let's think about that in the context of this problem below. So we want to prove that for any integer n, the expression n squared minus 5n plus 7 is odd. So how might we go about that? Well, in this particular case, I think I may try, considering whether n is even or odd as 2 separate cases. So let's start off by letting n be an integer. And we're going to consider the 2 cases where n is even and n is odd. So maybe to format this thing up, we'll say case n is even here. Now the reader knows that we're considering that case. So suppose n is even, then there exists some k such that n is equal to 2 times k. And now the expression that we're wanting to show is odd, n squared minus 5n plus 7, is the same as 2k quantity squared minus 5 times quantity 2k plus 7. And we'll work with this and try to show that it is of the form 2 times an integer plus 1. So this is 4k squared minus 10k plus 7. And I could think of that as 4k squared minus 10k plus 6 plus 1, because we need to get that plus 1 out there for our expression to have that form 2 times an integer plus 1. So now I can take those first 3 terms and pull a 2 out, and I get 2 times 2k squared minus 5k plus 3 plus 1. And I'm going to point out, just for emphasis, that 2k squared minus 5k plus 3 is an integer on account of on account of k being an integer. So our expression here, n squared minus 5n plus 7, has been written as 2 times an integer plus 1. So that's what it means to be odd. Okay, and now we need to consider the case when n is odd separately. So I'll continue on to the next page here. So let's do the case where n is odd. So here we suppose n is odd. There would exist some integer k such that n is equal to twice k plus 1. And we'll do the same sort of thing as before. We'll substitute that expression for n into the expression n squared minus 5n plus 7. And we'll multiply that 2k plus 1 quantity squared out, and you get 4k squared plus 4k plus 1. Distribute that negative 5, and you get minus 10k minus 5. And then there's a plus 7. And I see that the constant term here is really just positive 2. So this is the same as 4k squared plus minus 6k. And then I'll get a plus 2. And there's also a plus 1 there. So I'll just write it like that. And then I can factor a 2 out of those first three terms to write it in the form 2 times 2k squared minus 3k plus 1. And then I have a plus 1. And I'm going to point out that the term in the parentheses there is, in fact, an integer. And now we can see that our expression n squared is odd again. I guess above I actually misspoke and said n is odd, but what I meant to say there was n squared minus 5n plus 7 is odd. Let me correct that real quick. Right, because we took n squared minus 5n plus 7 and we wrote it 2 times an integer plus 1, we knew that it was odd, and that finishes the proof. You know, this proof would have been hard to do without knowing something about n, right? If you just take n squared minus 5n plus 7, the expression that you're trying to show is always odd. If you don't know something about n, you don't have any way to express that as 2 times an integer plus 1. So that gave us a little bit of extra information when we knew either n was even or n was odd, so that we could substitute and have something to get our hands on. So anyway, that's the way a proof by cases should look. You use some formatting to make it clear what the cases are, and then you do each one in turn. So why don't you try a proof by cases? In this particular problem, you're going to prove that if 3 does not divide n, then 3 does divide 2n squared plus 1. I'll give you a little hint here. If 3 does not divide evenly into n, what are the possible remainders? And you can use those remainders as the basis of your cases for your proof. So give that a whirl. Take 10 or 15 minutes or so. Hit pause on the video. And when you come back, we'll work through it together. All right, welcome back. So let's work through this together now. So let's start by assuming the hypotheses of the problem here. So let's let n be an integer, and let's suppose that 3 does not divide it. Then we can use the division algorithm. When you divide 3 into n, there's going to be some quotient and some remainder, where the remainder is between 0 but less than 3. But since 3 does not divide n, we know the 0 is not the remainder, because if 0 were the remainder, then 3 would be dividing n. So let's say it like this. There exist integers q and r such that, n is equal to 3 times q plus r, where r is strictly between 0 and 3. R is not equal to 0 here because 3 does not divide n evenly. Thus, r can only be equal to 1 or r is equal to 2. So we're going to consider those two cases separately, where r is equal to 1 and r is equal to 2. Okay, so first let's do the case where r is equal to 1. So if r is equal to 1, then we know that n is equal to 3 times q plus 1. Just using what we knew right here, that n was equal to 3q plus r, but our r is equal to 1, so we end up with this. Okay, so now that we know what n looks like, we can consider what 2n squared plus 1 looks like, because we're wanting to argue that 3 divides 2n squared plus 1. So what we're trying to show here is that 2n squared plus 1, we want to show that it can be written as 3 times some integer, right? So what we're going to do is take what we know n is equal to and substitute it into this expression 2n plus 1, and hope that after we do that we can pull a 3 out. So let's give that a whirl. Then what we see is that 2n squared plus 1 would then have to be equal to 2 times 3q plus 1, quantity squared plus 1. And we'll multiply all that out. We'll get 2 times 9q squared plus 6q plus 1. And then we still have that plus 1. And let's see, that would be equal to, 18q squared plus 12q. And then there's a plus 2 and a plus 1 plus 3. And then I see that I can pull a 3 out of that. So that's 3 times 6q squared plus 4q plus 1, where the expression in parentheses is an integer. Thus we know 3 divides this 2n squared plus 1 on account of the fact that we took 2n squared plus 1 here and we wrote it as 3 times an integer. That's the definition of what it means for 3 to divide something, right? Is that you can factor a 3 out of it. And then the second case we'll handle in a very similar fashion. It's almost identical. The algebra is a little bit different, but basic same idea. So if r is equal to 2, we have n is equal to 3 times q plus 1, and substitution into 2n squared plus 1 yields 2n squared plus 1 equals 2 times 3q plus 2 squared this time plus 1. So that's 2 times 9q squared plus 12q plus 4 plus 1, which that'll be 18q squared plus 24q plus 8 plus 1 plus 9. So that's plus 9, which is equal to 3 times 6q squared plus 8q plus 3, where the expression in parentheses is in fact an integer again. Thus again we have 3 divides 2n squared plus 1 again. And having checked that the result is true for all of the cases, then we see that the result's true in general. So that's the proof. All right. So the last thing we're going to talk about when it comes to proofs is proving and disproving quantified statements. So there's 2 kinds of quantified statements. There's the existential quantification and the universal quantification. And we're going to talk about both proving and disproving. But you know, whenever someone says to prove something and they also say to disprove it, disprove means to prove something is false. So one thing to keep in mind is if you want to prove something is false, it's the same as wanting to prove that the negation of it is true. So disproof and proof are just 2 sides of the same coin. Disproving something is just proving that the negation is true. So let's start with proving universally quantified statements here. And I'm calling this the direct method. So in the direct method, you pick an arbitrary unspecified element, x, in the universal set U, and then you just prove that p of x is true for that arbitrary unspecified element. So since when you pick x, you don't specify it, and it could represent any one of them, proving it for this arbitrary one is, proving it for all the possible values of x at the same time. So you don't have to do a different case for every element in the set U. You just pick an arbitrary one. So, for example, we could prove a fact that we've been using for quite a while, that for every integer n, we can say either n is even or n is odd. So how would we go about proving that? So to prove this, what we're going to do is take advantage of the division algorithm. Using this method that I'm outlining above, I want to start my proof by starting with an arbitrary unspecified element in the universal set. And since we're talking about integers here, my universal set U is just the set of integers, Z. So I'm just going to start by saying let n just be an arbitrary element of the integers. Okay? And now I want to prove that this arbitrary unspecified element is either even or odd. So what I'm going to do is use the division algorithm here. So by the division algorithm, upon division of this unspecified integer n by 2, there exist integers q and r such that n is equal to 2 times q plus r, where r, the remainder, satisfies this inequality. So if r is an integer and it's bigger than or equal to 0 but strictly less than 2, that just means that r has to be either equal to 0 or 1. Well, if r is equal to 0, we have this expression here, n is equal to 2 times q plus r, and if r is equal to 0, we see that n is equal to 2 times q, so n is even, or if r is equal to 1, then we have n is equal to 2 times q plus 1, again relying on this expression right here, that n is equal to 2 times q plus r, and we see that that is odd. Thus, if n is an integer, n is even when the remainder is equal to 0 when you divide by 2, or n is odd when the remainder is equal to 1 when you divide by 2. All right? So the key thing to understand is that, the big strokes of this proof was we started with an arbitrary element of this universally quantified statements, universe of definition, and then we arrived at the conclusion here for that arbitrary element, which is that n is even or n is odd. All right. One thing we can do if we want to prove a for every statement is to suppose not. So when I say an indirect method here, I'm talking about maybe doing contradiction. Remember, not for every x in u p of x is logically equivalent to there exists an x in u where p of x is false. If I wanted to do a proof by contradiction, so proceeding by contradiction, you could, one, assume for every x in u, p of x is false. That is, assume there exists an x in the universe such that not p of x is true. Then two, find a contradiction. Three, then you would conclude for every x in u, p of x is true. All right, so let's try an example of this type of indirect proof of a universally quantified statement for this example here. Prove that for all real numbers x, if x is strictly between 0 and 1, then x squared is less than x. So this is a statement of the form, for every x in the reals, 0 less than x less than 1 implies x squared is less than x. So it's a universally quantified statement. And so if I want to prove it indirectly, I'm going to suppose that that's false. And so negating it would give me there exists x in the reals such that 0 is less than x less than 1, and the opposite is true for x squared being less than x. It would be x squared is greater than or equal to x. So what I would do is assume that this is true and try to derive a contradiction. So let's do that. Proof by contradiction. Suppose to the contrary that there exists some x in the reals such that 0 is less than x is less than 1, and the conclusion is not satisfied, and we have x squared is greater than or equal to x. Now, x squared being greater than or equal to x would imply that x squared minus x is bigger than or equal to 0. And if I factor the left-hand side, that would be x times x minus 1 is greater than or equal to 0. But 0 is less than x is less than 1 implies two things. Certainly x is greater than 0. And two, it tells me that x minus 1 is less than 0. Since x is less than 1, right? If you just subtract 1 from both sides of that inequality, then you get x minus 1 is less than 0. So in other words, x is positive, but x minus 1 is negative. Well, this implies that x times x minus 1 is in fact less than 0, because a positive times a negative is negative, right? But that's a contradiction. This contradicts the hypothesis that x squared is bigger than or equal to x. Because if x squared is greater than or equal to x, then we get the opposite inequality here. And so we've reached a contradiction, and that's the proof. Now, I have to admit, this is a really bad contradiction proof, because I could have more easily proven it directly. Notice that on the strength of the hypothesis, 0 being less than x and x being less than 1, I could have arrived at this inequality directly without even using the hypothesis that x squared is greater than x. But then once you have that inequality, you've essentially proven the thing that you wanted to prove directly. So this was sort of an unnecessary proof by contradiction. But setting that aside, you see that in principle it's possible that if you want to prove a universally quantified statement, you can prove it by contradiction, which has the effect of converting it. The hypothesis you take when you do proof by contradiction would convert the universally quantified statement to an existential statement, which might make it easier to deal with. In this case, it didn't really help, but at least it shows you the mechanics of how you'd go about it. Okay, another thing we want to talk about is how to disprove a universally quantified statement. Well, this comes back to the logic of negating the universally quantified statement as well. So if you want to disprove that, for every x in U, P of x is false if the negation of that is true, i.e. if for every x in U, not P of x is true. So if you want to disprove for every x in U, P of x, you only need to demonstrate there exists a single element of U for which not P of x is true. In other words, for which P of x is false. And such an example is called a counterexample. So in other words, if you want to disprove a universally quantified statement, you just got to find a single counterexample to disprove it. So there's a lot of examples of this sort of thing where you can disprove universally quantified statements. Here's a simple one. Let's disprove that for all x in the reals, the square root of x squared is always equal to x. You may be confused at this point thinking, what? That's certainly true, isn't it? Every time I take the square root of x squared, I should get x because square roots and squares cancel each other. But it's not quite true. Let me give you an example of why it's not true. Well, consider x equals 1. I'm sorry, x equals -1, which is certainly a real number. We have square root of x squared would equal the square root of -1 squared in this case. And inside that radical, I've got just the square root of 1 now, which is equal to 1. But that's not equal to -1, which is our original x value. So square root of x squared does not equal x when x is equal to -1. And so a counterexample of this is x equals -1. There's lots of other ones that you could do that are like this. Like there's lots of algebra mistakes that beginning calculus students tend to make. There's this one, the square root of x squared plus y squared equals x plus y. Oh, and of course there's always x plus y. When you square that, you just get x squared plus y squared. No. And you could disprove that, these statements like this are not universally true for all x and y, because all you'd have to do is demonstrate the existence of a pair of numbers x and y for which it's false. And then the last couple of observations here. If you want to prove an existential statement, all you have to do is demonstrate that a single element of the set exists for which P of x is true. So prove that there exists an even prime number. Okay, proof. Consider n equals 2. N is even because 2 is even and 2 is prime. The only way to factor 2 is that's 2 times 1, so it's not composite. So that's it. And then if you want to disprove an existentially quantified statement, you just need to prove that its negation is true. So in other words, you want to show that for every x in U, not P of x is true. In other words, for every x in U, P of x is false. So consider this following problem here. There exists a natural number such that n squared plus 3n plus 2 is prime. So I'm going to give you a proof by contradiction. Well, not by contradiction, but I'm going to show that the opposite of this statement is true. So I'm going to let n be an arbitrary natural number. So I started with an arbitrary natural number n, and now I can just say, well, for that arbitrary natural number n squared plus 3n plus 2 can be written as, we can factor that as n plus 1 times n plus 2. Well, because n is a natural number, n is bigger than or equal to 1. So n plus 1 is bigger than or equal to 2, and n plus 2 is bigger than or equal to 3. Well, we happen to know that the smallest even prime number is 2, or the only even prime number is 2. So at this point we know n squared plus 3n plus 2 is greater than or equal to 6. And further, either n plus 1 or n plus 2 is even. So n squared plus 3n plus 2 is greater than or equal to 6, and n squared plus 3n plus 2 is even, because it's a product of an even number with the product of an even integer with any other integer is still going to be even. So thus, n squared plus 3n plus 2 is not prime for all natural numbers n. So see, we have disproven that there exists an integer n, or a natural number n, such that n squared plus 3n plus 2 is prime, because we considered all possible natural numbers and proved that for none of them that expression is prime. All right, so anyway, moral of the story here is that to disprove something, all you need to do is just prove the negation of it is true. So disproving something is really just proving something else, proving the negation is true. So it's not really like it's a different thing altogether. Disproving something is just a proving of the negative. Okay, so now I would like you to work on some problems. So I have some skills check problems here on proving and disproving quantified statements that I would like you to work through. And I've got a few problems here, 6 problems. Some of them you can solve and the answer is really short. Some of them take a little bit more work. So maybe figure on about 30 minutes to do these problems. So hit pause, try to work these up, and then when we come back together, I'll work through them with you. Okay, welcome back. Let's have a look at the first one here. So the statement is, for all real numbers x and y, if x squared equals y squared, then x equals y. And you're asked to prove or disprove it. I bet you did not have a hard time with this one, but I do want to break it down a little bit. And let's just examine the logical structure of this. In its more symbolic form, the statement is, for every x comma y element of the reals, x squared equals y squared implies x equals y. Now, if you think that this statement is true, then you would need to pick 2 arbitrary elements, x and y, from the real numbers, and then argue that this implication is true. And if you think it's false, the negation of it is there exist x and y in the reals such that x squared equals y squared, and at the same time x does not equal to y. So if you're disproving it, then you're going to prove the negation. And in this case, we are going to prove the negation. In fact, what's your counterexample? Well, you can come up with a number of counterexamples. So our counterexample is, I know that 1 squared equals -1 quantity squared, but 1 does not equal -1. So x equals 1 and y equals -1 is a counterexample. But notice that in doing a counterexample, we're really proving the negation, right? We showed that there exists an x and a y in the reals such that the squares of the 2 numbers are equal, but the 2 numbers themselves are not equal. Okay, for number 2, we're looking at the statement, for all integers n and m, if m and n are even, then m plus n are even. So if you think it's true, you need to prove it. If you think it's false, you need to prove that also. This is another universally quantified statement. So the logical structure is, for every m and n in the integers, m and n even implies m plus n is even. And the negation of it would be, just like before, that the for every would become an exist, and it would be, there exists an m and an n in the integers such that m and n are even, but m plus n is odd. In this case, though, it's true. The statement as it is true, and so then we need to prove it. So proof. So since it's a for all statement, we start with 2 arbitrary elements in that domain of discourse. So we're going to say let m and n just be 2 arbitrary elements of the integers. And then we'll suppose that the hypothesis of the conditional statement is true. So suppose m and n are even. So now we've assumed the hypothesis of this conditional statement is true, and we want to argue that the conclusion follows as a consequence. of our hypothesis. We know m and n are even, so then there exists integers k and l, such that we can write m is 2 times k and n is 2 times l. And now we can look at the sum of m and n. M plus n is equal to 2k plus 2l, which adds up to 2 times k plus l, where k plus l is an integer. So m plus n is even, being expressed as 2 times an integer. Not too bad. Okay, number 3. For all natural numbers, 2 to the n plus 1 is prime. This one's actually a little tricky. So if you just get your calculator out and start messing around with it a little bit. So if n is equal to 1, let's make a little table here. Okay, when n is equal to 1, then 2 to the n plus 1 would be 2 to the 2 plus 1, so that'd be 5. And then we could ask, is that prime? Yes, 5 is prime. If you put 2 in for n, you get 2 to the 4, so that's 16 plus 1, so 17. Yeah, that's prime. These numbers get big pretty fast. 2 to the 3, so that's 2 to the 8th plus 1. So 2 to the 8th is 256 plus 1 is 257. And yeah, that's prime. It turns out when you put 4 in here, you get a rather large number, which I punched into my calculator, and I discovered that it's 65,537. And it turns out that, yes, that is a prime number. It's not until you get to n equals 5 that you get this ginormous number that is not prime. Now, what I did to discover that this number was not prime, I used the computer. I went to Wolfram Alpha and punched in 2 to the 5 plus 1 and said, is this prime? And it said no. And it said how you can factor it. So I'm just going to say C Wolfram Alpha. But the point here is, though, is we have found a counterexample, right? So the original statement was for every n in the natural numbers, 2 to the n is prime. The negation of it is there exists an n in the natural numbers such that 2 to the n is not prime. And we have just demonstrated that the negation is true. So we have a counterexample of n equal to 5 to the original statement. The original statement is not true because I had the counterexample of n equals 5. Okay, so number 4 here, we have an existential statement, and we're being asked to prove or disprove it. So what do you think? Do there exist real numbers x and y such that the square root of x squared plus y squared equals x plus y? Sure. There are a few different ways that this can be equal. Consider x and y both equal to 0. Square root of x squared plus y squared would be the square root of 0 squared plus 0 squared, which is square root of 0, which is equal to 0, which is the same as 0 plus 0, which is equal to x plus y, right? So when you're trying to prove in the affirmative an existential statement, you only have to give one example for which the statement is true. You could also do x equals 0 and y equals 1, or the other way around, x equals 1 and y equals 0 would work too. Now you may ask the question, well, how many distinct pairs of solutions for x and y are there? Well, that's a separate question. I'll leave it to you to explore that question. And then number 5 is sort of the other side of the coin for this question. Is it true that for every x and y in the reals, square root of x squared plus y squared equals x plus y? I'm going to have to say no. And the proof of my answer is that I can come up with a counterexample. Consider x equals 1 and also y is equal to 1. Square root of x squared plus y squared would equal the square root of 2 in that case. But x plus y equals 2. And since square root of 2 is not equal to 2, we have square root of x squared plus y squared does not equal x plus y. So we demonstrated a counterexample to the universally quantified statement. And the last problem here, number 6, this one's a little tricky looking, but is it possible that you can find an x and a y in the real numbers such that x squared plus y squared minus 8x minus 6y plus 24 equals 0? So this is a little bit of an algebra challenge for you, but you may remember the process of completing the square, and you may recognize from previous algebra classes that this is actually this has the form of the equation of a circle. This one's a bit tricky on the algebra, and in fact, I just noticed that there's a little mistake in the problem, so I'm going to erase that 24 and replace it with 26. This one's a bit tricky, so the question is, does there exist a pair of numbers x and y, where x squared plus y squared minus 8x minus 6y plus 26 equals 0? Well, it's tricky, but you may remember back from previous algebra classes that you can do this process of completing the square, and when you see equations that look kind of like this, you can try to, you may recognize that it has the general form of the equation of a circle. So let's do this completing the square business, and we'll see that, yeah, it doesn't work. So no, and the proof of it is, the negation of the statement would be for every x and y, that expression is not equal to 0. So I'm going to let x and y be any two arbitrary real numbers. Then the equation x squared plus y squared minus 8x minus 6y plus 26 being equal to 0 is equivalent to the equation. Let's see, here's where I do the little completing the square business. X squared minus 8x, let me leave a little space there. Then I got plus y squared minus 6y. Let me leave a little space next to that. And then I have plus 26 equals 0. And so the way you complete the square here is for the x terms, you take half of the coefficient of x and square it. So half of negative 8 here is negative 4. Square that and add it in, and you get plus 16. And you do similarly with the y terms. You take half of the coefficient of y, which is negative 6, divided by 2, you get negative 3. Then square that and add it in. So I'd add in 9. But notice here that what I've really done is add 25 to the left-hand side of this equation. So to make the books balance, I have to add 25 to the right-hand side as well. And then the point of doing this is that the x terms, I'm going to use parentheses here just for emphasis. But the terms in the first set of parentheses is the same as x minus 4 quantity squared. And in the second set of parentheses, that's the same as y minus 3 quantity squared. And then if I take the positive 26 on the left-hand side and subtract it from both sides of the equation, I get negative 1 on the right-hand side of the equation. But this equation now clearly has no solution because since those squared terms have to be greater than or equal to 0, x minus 4 quantity squared and y minus 3 quantity squared are both greater than or equal to 0 for all x and y in the reals. So the only way that the original equation would have a solution is if this equation that I reduced it to has a solution, but the equation that I reduced it to has no solution. So the original equation has no solution. Okay, that's it for sort of our basic proof techniques. Invariably, there will be some things that come up that maybe didn't get totally covered by this. There's lots of little exceptions and things to watch out for. But as we progress, we'll encounter these things and deal with them as they come. And we're going to learn more specialized proof techniques as we move along. The next chapter of the book that we're going to cover is about sets. And so we're going to learn some techniques that specifically apply to proving things about sets. Like how do you prove two sets are equal? How do you prove one set is contained in another set? Like that. And then when we move later on to functions, we'll learn some techniques that apply to proving properties about functions. But what we've covered so far are sort of general proof techniques that apply to any sort of situation whatsoever, any kind of mathematical proof that you might want to do, regardless of what the topic is. So we're going to specialize a little bit now moving forward. But we will keep using these things that we've learned in the last few videos all the way through. So the basic logic, understanding what the logical structure of a statement is, so that in case you need to negate that, you'll know how to do it. So you need to know those tautologies for how to negate statements. You need to know how to deal with quantified statements. So like when you negate a for every statement, it becomes a there exists statement, that sort of thing. This is all going to be super useful as we move forward. All right, we'll stop there. We'll see you soon. Bye.